Thanks for your kind introduction. Thanks very much. Yeah, so I'm going to talk about individual different clustering. Hopefully, I won't keep it very much. Okay, so by now you know, or that you know about the clustering, there's a fundamental problem, but by now it's very well. So, and in particular, high level, the idea is that we want to just partition points into a set of clusters such that the points in the same cluster are more similar to each other compared to the points in other clusters. Okay, and the model that I'm considering in this talk is centroid-based clustering. So basically, we would like to choose centers and assign each point to the closest center. And we usually, once we have a centroid-based clustering, we usually take care of some global objective of the popular one like K-center, K-median, and K-max. So, you already decided in the previous slide, but let's see, just go over quickly. So in the centroid-based clustering, we want to partition the set of point P into K parts, and is to come up with a set of centers and a mapping between the points and the centers, right? To minimize some global objective. K-center is just, we want to minimize the maximal distance of any point to center. In K-median, we want to minimize the sum of distances, and in K-means, we want to minimize the sum of the square distances. And as we see also in the previous presentation, so basically K-center is at infinity, K-median is L1, and K-means is just corresponding to minimizing those norm of distances. And in general, we can think of LP objective, right, as was the case in the previous presentation. So we want to minimize the LP distances, the P norm distances of points to their closest centers. Okay, so it's our empty hard, and we know constant factor approximation in the standard setting. That's fine. But now today I want to talk about the fairness of clustering, and in particular about the individual notion of fairness. But before that, you may have heard of different notions of fair clustering. And maybe it's just maybe before going to the individual fairness, let me recap. What are the notions? And in particular, say why we are dealing with too many notions. So I guess the underlying answer, or the main answer to this question, is that because clustering has various applications, and in each application, it's just a different notion of fairness makes sense. So basically, depending on the application, the fairness will lead to a different problem, and then you need to deal with a different constraint or objective and solve a different problem. So that's basically the reason. And to give you some example, for instance, one of the main applications for clustering is partition. So you are given a set of points, and you want to assign some benefits to the group of, you want to partition the points and assign benefits to them. For instance, you can think of you want to decide about the loans and which loan packages to be assigned to which group of people. Or even in some application of clustering in machine learning pipeline, when we want to basically to add some feature to our set of points. So basically what's called feature engineering. So in this set of application, clustering is also commonly used. And the way it works is that we do a clustering and then add the center as an extra feature for the set of points, and thus just feed it to the downstream application. So basically, if you are not careful here, then you may create some biases if some fairness requirement is not satisfied. Okay, so this is one application. Another canonical application for clustering is perhaps data summarization, where basically you want to pick K-centers and treat them as a summary of the whole data set, right? So basically, then it matters how these centers are representing the whole point set. So basically, then you care about the distances of point to their centers, and the cost of each group is the measure that matters for us for the fairness. And it's used, for instance, in text summarization in search result. For instance, you search for some query in Google search, and let's say for scientists, and you expect to see a proportional ratio of female scientists and male scientists in the answer. So these are the type of fairness that we carry in these applications. Or, I mean, a very standard popular problem in theoretical computer science and operation research is facility location. So here, you basically would like to open a fixed number of facilities, or I'm talking about the clustering version. So you want to open a fixed number of facilities, and you want to just minimize the service cost to the client. Okay, so these are basically the application. And just since I'm talking about individual fairness, let me just briefly say what are at high level, what are the notions of fairness we care about. So the first, I mean, the one is group fairness. So basically, here we would like to satisfy some sort of statistical parity between the, let's say, the error, the accuracy of the, for instance, the prediction for protected groups that are determined by gender base or other protected attributes. And in general, we would like to provide some equal proportion of each protected group in each outcome class. This is in the sense of classification. So basically, equal opportunity to group as a whole, in a sense. But in the individual notion of fairness, we would like to basically, the underlying goal is to treat similar individuals similarly. So again, in a classification type of version is, for instance, if you have a set of qualified candidates, let's say the hiring, then you want to make sure that your process provide equal chance for each of these qualified candidate to be hired or to get offered, for instance. Okay, so these are the two very general type of notion of fairness that we usually consider. And for instance, for these application, people have a look at this type of fair clustering problem. For instance, for the partitioning, when the ratio of each protected group in the class clustering matters, people have studied fair representation clustering. Many people here in this room, even Samir has some great work with this problem. And for data summarization, you can think of, for instance, the notion that Eden talks about in the previous talk, or in the facility location again, the type of problem that Eden talks about, or I can, and I will also mention one of the individual notion of fairness that is related somehow to the facility location problem. So, any questions so far? I mean, it's just about modeling background. Okay. So yeah, let's think about the individual fairness for clustering. So what's the idea here? So here I'm thinking of a facility location type problem, and I want to just open some facilities. So if I just tell you that I'm going to pick K centers, or I'm going to open K facilities, then without any prior knowledge, each point will expect to see a center amongst its n over K's closest neighbor. So as if, for instance, the city announced that I'm going to open K hospitals, then I mean it's a fair expectation for different communities, or let's say different neighborhoods, to see at least a hospital among its n over K closest neighbor. So why it makes sense? It basically says that if you are a denser, as the neighborhood becomes denser, then you will see some facility in a closer neighborhood. And this makes sense because the expectation of being close is different based on the density. For instance, if you're in a rural area, 15-minute drive, I mean, is basically fairly close by distance. But if you're in a populated downtown, I mean, I don't know, New York, then it's really, I mean, you cannot, I mean, this 15-minute walk is something that's close, or maybe 10-minute walk is something close. So basically, it's a reasonable assumption to say that the expectation for different individual is different. And this basically, this density can be captured by the radius that contains the n over k closest neighbor for each point. Okay, and so that's formally the problem. So we are a collection of endpoints. Then we define a fair radius for each point, which is basically the distance of point to its n over k closest neighbor. N over k is -1, but just, or n over k, it's more or less. And we say that a k clustering is fair if the distance of everyone to its closest center is at most within the fair radius of the point. Okay, so this problem was introduced by Jung, and Lutz. I'll talk more about them, the work, but they show that basically, this is a nice formulation, but the problem is NP hard. Basically, it's NP hard to decide whether such a clustering exists or not. And this has motivated a more relaxed version of this problem, which we call alpha fair K clustering. So basically now we want to find K center such that each point B has a center in distance at most alpha times its fair radius.
So I was just wondering about the formulation. I guess the other way of formulating it is to just say, for every point, I look at its close center, something, and then you want to maximize the minimum. Minimize the maximum distance to its own center. Right? But that sounds, I guess, a little like
K center.
K center. I forget the name of the question.
Yeah, it's like more like a K center, and actually you'll see that it's basically this somehow is a special case of weighted K center, for instance, or what is called what's known as priority K center problem.
But so the advantage of this formulation is that somehow you still might. There may be points that are very far from everyone, in which case K center doesn't do anything interesting or something.
You want still I guess all these K center, K median, or K means they can be basically the price of fairness can be unbounded for any of these standard algorithms. So there are instances that K center can violate, for instance. Basically, this could be the case when, for instance, you have a very dense set of points, and the K center has, for instance, choose to not cover this point. There could be you can come with an instance like this. If you want to.
But this formulation avoids it or something?
You can get basically the fair solution. Okay, so I mentioned, this notion was introduced by Jung, and Lutz. Basically, they show that you can always find the two fair solution, which basically you can find K center such that every point will see a center at distance at most 2 times its fair radius. And interestingly, if it was somehow implicit in some earlier work on metric embedding, for instance, one by Charikar and Urian-Kostia, and one by Chen, Denitz, and Gupta. So it seems to be interesting notion in the sense it has some other application as well. To come with this structure, you find the centers in a certain radius around the points. And as I mentioned, it's also a special case of another known problem, priority and weighted K center, where basically there you are given some radius for each point, which is radius of interest for each point. This could be anything. And you want to minimize the maximum of violation of this radius. You want to pick K center such that the distance of each point to its closest center over this radius that is given for each point is minimized.
Sorry, what were those 2 papers trying to study?
So this was, for Urian-Kostia, it's like global local embedding, right?
Unrelated to this study.
Yeah, it's completely. Okay, and this paper is, this problem itself is also studied in literature, and for instance, it also the recent work Chakrabarty, Chakrabarty, Gahwani, where they look at an outlier version of this problem. This itself is an interesting question. Actually, another interesting question that's related to summations, if anyone is interested, is called chance K coverage problem. So basically, it's basically the probabilistic version of the problem. Basically, it says we want to find a probability distribution over the set of centers such that for each point, there is a center at distance at most R of V with that probability that is given for so we have probability PV for each point V, and we want to pick a distribution over a set of centers such that for each point with probability P over V, we have a center at distance at most R of V. So, I mean, these two problems both have constant factor approximation. Yeah, but I think it's interesting, for instance, to look at them under more general assumption, like what happens under the fairness, for instance.
I have a question.
Sure.
So, weighted case center, isn't it the same problem? Like, what's the difference? This R of V doesn't have an over K.
Sorry, no.
Isn't it the same problem? Like all this priority.
Sure. You know, it's more general problem than what you're considering. The priority.
So the RV is.
The RV can be anything, but if you set RV to the fair radius, then it becomes just a fair clustering problem. Was it your? Did answer the question?
This RV is different from the L over K.
Yeah. In this priority or weighted case center, you can pick any radius, any RV can be anything.
That's the same R for everything.
But what? Sorry.
So is RV and part of the input?
Yeah. In this problem, in the weighted in the priority case center problem, yes, RV is part of the input. I just want to mention that this fair clustering is also can capture as a special case of this, and you will see. I mean, why I'm mentioning it in the data talk, because we can also solve this problem. Okay, but the catch is here. I mean, this problem were studied before, but they were just trying to find a feasible solution. Basically, they were trying to find a feasible fair clustering. So our motivation for this work was to see if we can optimize, if we can look at the optimization variance of the problem. So we want to come up with a fair clustering that minimizes some global objective, like K-median, K-means, or in general LP norm. Okay, and this is what we consider. So basically, one thing that I was mentioned before, so the price of fairness is unbounded for this fair clustering. So basically, if we want to look at the optimization version, it makes more sense to look at the best fair clustering solution. You cannot compare it to the best clustering solution. So now we want to find an alpha fair clustering with minimum global clustering cost. That's our goal. And I thought the objective can be K-median, K-means, K-center, and so on. And okay, so we know that actually the problem itself is NP hard, or at least for when alpha is 1, right? And actually it's even hard, I guess, when alpha is between 1 and somewhere between 1 and 2. I forgot the exact value. So, but this basically motivates that we can instead come with a bicriteria type approximation. But it's still a good question. What happens? Alpha is large. If we can get a pure approximation, that's we don't know. So, but in general, what I'm presenting here is a bicriteria type of approximation, which is beta and gamma, and it means that the solution that I'm returning has cost at most beta times the optimal alpha fair solution for the instance. And each point will see a center in distance at most gamma times alpha times its fair radius.
Sorry, in this price of fairness, the unboundedness of the price of fairness, you've mentioned before that the standard case center is as unbounded price of fairness, but this is true also for this fairness radius version. That's zero unbounded.
Oh yeah. It's actually for this instance, which is a special case. Okay, so, and this is basically the summary of the result that we know about this problem. So we initially, with Safid and Mahabadi, we show that the local search algorithm can give a constant factor approximation for k median and k means. And this will give order of log n and 7 approximation for k center. And basically, in general, for general LP norm, it gives order of p and 7 approximation by criteria. And then there was two kind of parallel work that showed that you can actually adapt the LP-based approaches and get basically constant factor approximation for everywhere. So basically for k-center, also improving over the constant factors. And yeah, I will mostly mention the local search result and a little bit about our LP-based approach. But I can very briefly say what's the outline of all of these algorithms. Okay, so basically this is the outline of our algorithm, and it has in a high level it has 2 steps. So the first one is that we need to come to some set of critical balls that's almost using all of these 3 algorithms that they described. So, and this is the definition for the critical ball. So we want to, given point set P, we would like to find a set of L critical balls, that L is smaller than K, such that these balls have this property. So basically they are disjoint, and for any point in P, the distance of V to its to one of these centers, sorry, to C1 to CL, is at most is of order of alpha times its fair radius. Okay. So basically, if you just return these L points, I mean, you get the order of an approximately alpha fair solution. Right. So let's see, I mean, how the algorithm works. I mean, the algorithm is also using the paper of Yuri and Kustian, I guess, the previous paper as well. So the way that it works is that we start with a set of point P, and we pick the point that has the smallest fair radius. Okay, so basically the densest one, the one that has the densest neighbor around it. And then we remove all the points such that the distance of V to this center C is less than 2 times its fair radius. Okay, so let's see now just quickly. But it says here, I mean, this is our first choice. This is the center I pick the blue point as a center, and then the ball is the fair radius for the point, and those 2 gray points are also covered by this point, and we just remove them from the consideration for the next step. And then we continue with the next point in the data set that has the lowest fair radius, and continue the process. Okay, so basically, the claim is that any set of K-center that intersect with these critical balls is order of alpha fair. This is somehow the key observation. So why is the case? I mean, it's basically follow the triangle inequality. Just for completeness, for each point V, let's CV to be the first center that capture V in this process. So basically, CV is the first center such that the distance of V to CV is less than 2 times its fair radius, 2 times alpha times its fair radius. Okay, and let's see prime V be the center that is picked from the ball center at CV. So I assume that I'm picking a set of centers that intersect all these critical balls, right? And let's C prime V be the center that is picked from one of the centers that is picked from that critical region. Okay, then the distance between B and C prime B is order of alpha times RP, and it just follows a triangle inequality. right? It's follow triangle inequality and the way that we pick the centers. Okay. So basically, I mean, we first find these critical balls, and then we try now this is our problem. We want to find K-centers that intersect all these critical regions. Okay, and I claim that if I have a good approximation,
what do you mean by centers intersecting?
Yeah, I mean, if we pick a center from each ball.
That's it.
That's it. Yeah. Okay, so and this is somehow clear, right? So the first part that I show that any set of K-centers that intersecting with the critical balls is order of alpha pair. That was the previous slide. And it's also easy to see by just by the fairness requirement. Any alpha pair solution has to pick centers that intersecting these critical balls. Because just looking at the requirement for the centers, you need to pick someone from that radius. Okay, so it's so that makes sense. I mean, if you have a good if you have an approximation algorithm here, then we are done. And this is where people, I mean, different group have picked different approaches. So the first one is a local search approach. So I mean, it's a standard things for the clustering problem. Just basically show that this local search work here. So here, I mean, there is a bit small, somehow challenge part is to come with a good initial first solution. And to do that, actually, we also use another somehow existing method. So we follow the greedy type algorithm for K-center here, which is also known as Gonzalez algorithm. So we first pick the centers for the critical balls, and then in the remaining iteration, we just pick a point that is furthest from the current set of centers. Okay, so we can show that this greedy approach is order of an approximation. And this is also not hard. I mean, let's see with the set of selected center and C star be the set of
order of an approximation with respect to.
So now I'm looking at the problem that I want to pick K centers that intersect with all critical balls and have minimum global cost. Let's say K median cost. Yeah, I'm mostly talking about K median cost here, but for any LP objective, I mean, we will lose maybe just another factor of P or so, something polynomial. Okay, so C is a set of centers that we pick at the end of this greedy approach, and let C star be the set of centers for the critical balls that we construct. And let V be the furthest point from C. And let's mu be the distance of V to C. So basically, I know that for every point in P that is not a center, its distance with closest center is at most mu. Okay, so basically the cost of my solution is simply, it's easy to see that it's n times mu. And we can claim that optimal has also to pay at least mu over 2. And so the reason is that, I mean, I'm looking at the set of points C union V. Sure.
So the spectral centers of critical balls, is it the point which we should pick to draw this, like the ball? Is that stupid?
Yeah. That's exactly. So in any K clustering, I mean, we have a C union V is, I mean, K plus 1 point. So by pigeonhole, we have 2 of them will be mapped to the same cluster in the optimal clustering or any clustering. And also we know that the P1 and P2 can only, at most one of them can belong to C star, because I know that the balls are disjoint, and if P1 and P2 are in different balls, so they cannot be in the same cluster, because they will find someone closer to themselves in their own ball. So that's maybe just the only observation that we will add to the Gonzalez analysis, and then it will go through. And then we can show that the distance, since the distance of P1 and P2 is at least mu, then the distance of one of them to their closest center would be at least mu over 2. So the total cost would be at least mu over 2. So it's a very loose analysis, but I want just to get some order of an approximation, which is enough for my case. And then I just do the local updates. And so basically by local update, I mean, if there is a swap of size at most t that reduce the cost by a factor of 1 plus epsilon. So this is the type of local update that I'm looking for. So let's see it in example. I mean, ideally, I would like to check for every point in my set of centers and every point that is not in my set of center and see if I can exchange them and get a better global cost. But I mean, it doesn't work. It's not as simple here because we should also make sure that we keep 1 point in each critical point. So we cannot do all possible swaps. Basically, that's maybe the most technical or ad hoc part of the analysis. So basically, we should be careful about it. For instance, I mean, this swap is not feasible, but we can use, for instance, this swap. Because if we perform this swap together, then we still have 1 center in each critical point. Okay, so I'm not going to talk about this, but it's just it's somehow, if you're familiar with the local search analysis for the k-median or k-means, we still need to follow the same analysis, but we need to come with more complex combinatorial type of optimization for the analysis. So basically, there's some covering, some mapping for the points in any stable or close to optimal cluster and optimal clustering. So just some sort of combinatorial type analysis that's through the case analysis. Okay, so I'm not going to talk about it, but you can see the paper for details if you're interested. And actually, we didn't try to do it very, I mean, optimize basically constant factors, and there could be possible to get a better constant factor. But what we could show is that there's always a valid swap of size at most 4. If you are more than 1 plus epsilon times the optimal solution, then you can always find the swap of size at most 4 that gets some improvement in the local search. Okay, and then these together says that the algorithm terminate after order of log n over epsilon. This is why we care. I mean, I showed you the order of n approximation for the initial solution. And it's, I mean, we're looking at the swaps of size at most 4. So each iteration runs in order of k to the 4 times n to the 4. So overall, we have a polynomial type algorithm, and we get a constant factor approximation. So, okay, so yeah, that was the first approach, the local search. I didn't say maybe too many details about why local search is working, but that's morally the algorithm and the part that we need to care about for the algorithm part. Okay, now that was the first approach. Now let's think again about the problem. So what we wanted to see was we wanted to pick k-centers such that from each ball we are picking at least 1 center, and we want to get a minimum cost, right? So if you think about it, this problem is basically facility location under matroid constraint, right? Or it's very similar because basically you have some sort of it's not exactly, but you can convert it. So basically you want to make sure that you are picking 1 point from each critical box. So, and let's see how we can. Just before that, let's see what's the facility location on the matroid constraint. So we are given a matroid over the facilities, and we want to find a set of facilities that form an independent set in this matroid. Basically, we want our facilities to basically be an independent set of this matroid and minimize this object, which is the classical objective for facility location. We want to minimize the opening cost and also the service cost for the clients. Okay, so now let me show you how you can do it with how you can solve this problem with facility location on the matroid constraint. So basically, we look at our point set, and we define these partitions. So we pick our ball as partitions, the critical balls as the partitions, and we also pick a copy of all points as another partition, which I call P prime. And then this is the way I create my partition matrix. For each critical ball, I make sure that the solution picks at most 1 point from each critical ball. Okay, and for the copy, for the second copy of the whole points, I make sure that I'm picking at most k minus L points from this copy. So basically, this ensures that, I mean, if any solution has to pick exactly one from these critical balls, and k minus L points can be from anywhere else. There is no other way to solve this partition, to satisfy this partition metric. Okay, so now, I mean, that seems simple. And then we need to only set the opening cost per facility equal to 0. Then it becomes just a standard K clustering problem that satisfies the required the constraint that I was looking for. Okay, so that's simple, right? I mean, then we get then we need to just see what we know for this problem for different objects. For K-median, there's actually this paper that Shili talked about yesterday. So one of their results also implies 7.081 approximation for K-median under matroid constraint. And for K-center, there is a result by Jung and Nguyen that they gave 3 approximation. And in general, we can show that in LP norm, you will have a 16 approximation. So this basically for the LP norm is morally the result of Swami, but he proved it for K-median and K-means, but it's easy, honestly, to show that this also works for LP norm. It requires to work some work, but it's still okay. So basically, this was mostly what I wanted to talk about. And yeah, I just mentioned about the another work that also had some constant factor approximation for this problem. And they also follow the same approach. So they find the set of critical balls, and then they look at the LP approach by the Charikar et al. That Eden also mentioned in his talk. And they show that you can add a constraint that makes sure that 1 point from each critical ball is selected, and then just follow the rounding by Charikar. So this is another approach, but you get a slightly better approximation for the cost function, but worse approximation for the fairness constraint. Okay, so I want also to mention some other few notions of individual fair constraint. So there is another work by Anderson et al. That they say that they define the individual fair clustering as follows. Sorry, I forgot. So this one is that, so we want to come with a distribution of centers for each point in the data set. And they basically want that each similar points, which similar is defined based on their distance, have similar distribution. So basically, if V and U are close by in the data set, we expect that their distance, their distribution of their centers should be somehow similar, close to some, under some distance function that they're considering. So there's another work by Feindeser et al. That they consider individual preference stability. So basically, they say that, okay, each point look at its own cluster. Yep.
So the first thing is for algorithms, solutions.
No, therefore for solution. This is expect to be the solution. So basically, the output is a distribution over the centers, right? So each point will have a distribution over the centers that it's going to be assigned to. And they want that the distribution for 2 points that are nearby to be similar. And they're considering various different distance for both the similarity and the similarity of the solutions. So the other one is the individual preference stability. Basically, they said that we say, so it's more like a stability but has some connection to the fairness in a sense that they say that the point feels to be treated fairly if its distance to its own cluster on average is less than to its distance to any other cluster. Okay, it's have more basically motivation more comes from the game theory, but it has some very nice connection to the fairness as well. And there's another line of work that look at the pairwise fairness. So basically, they want that as the points are getting closer to each other, that the probability that they belong to the different clusters are getting smaller and smaller. So they're giving some function alpha that is defined based on the pairwise distances of points, and they want to come up with some clustering that satisfies this condition. This is also Samir is also part of this work, and another recent result is called alpha equitable type of fairness. So basically, here they assume that each point has some set of some subset of other points in the data set that he or she presumed those to be similar to herself or himself. Okay, so suppose I assume that, for instance, that table is very similar to me, then I expect that my clustering cost will be within alpha distance of those sets. This is another type of fairness that applies. Yeah, so basically these are four, in particular last two definition is they were trying to more maybe following the initial definition of individual fairness, which is saying that similar individuals should be treated similarly. So they're trying to formalize it more, what it means to be similar for the points and what we expect to be the similar treatment. So it's more like a supervised learning type of approach. Okay, so let me conclude with some open questions. So one question is if we can get a better analysis for local search. So right now our approximation factor is for k-median, and k-means is like 80 and plus 100, so it's not really interesting. I could improve it for k-median or k-means, I forgot, to something like 40 or 50, but still it's still not there. So maybe a good question here is if we can show that the certain swap of size 1 or 2 suffices for our analysis. So basically that's what empirical evaluation suggests, that you only need to look at those swaps. And maybe another interesting question that is related to the second approach, which was the facility location on the matroid constraint. So right now we are showing that the result of Swami for facility location can be generalized to LP norm. That's why we have to pay 16 in the approximation factor general case. But as I mentioned, there is a recent result by Krishna Swami, Lee, and Sandeep that showed you can get something less than 8 approximation for the k-median case. So now the question is if we can generalize it for the LP norm. It's not clear. Or if we can get better than 16, but I don't know. And in general, if you can get a better approximation factor or consider new constraints such as, for instance, this problem, fair clustering under outlier. And in general, it would be interesting to look at this problem in the massive data analysis model, like if we can come up with a scalable algorithms or in a streaming algorithm or so on. So yeah, that's conclude my talk.